Our Bellwether question for today is, why is the Atlantic Ocean getting bigger? We should be able to answer this question by the end of the lesson. When asked which mountain is the tallest on the surface of the earth, most people will say Mount Everest. But technically, that's not exactly true. Mount Everest is about 29,000 feet tall, but we actually have a taller mountain in Hawaii, Mauna Kea, that's almost 31,000 feet. The difference is this one is about 2/3 underwater. So here we have a map of Hawaii, and you can see Mauna Kea is here. This is just showing the parts of land that are above water. If we were to remove the water and actually see what it looks like down into the water, you would see that this mountain is actually coming from the seafloor all the way up, creating that island. So it is actually the tallest mountain. To give you a perspective of how tall this actually is, let's take a look at some famous, very tall mountains. We have Everest, Fuji, Kilimanjaro. Everest is extremely tall, but when you think about another mountain being almost 2,000 feet more, it's very, very, very tall. But again, 2/3 of it is underwater. So we're discussing seafloor spreading today. Just like the name implies, the seafloor or the ocean floor is spreading apart. By the end of this lesson, you need to be able to describe the process of seafloor spreading, give evidence to support it, and be able to identify the features on the surface of the earth that are created by this process. So to give you an idea of what was going on at the time that we started to find out about seafloor spreading, Alfred Wegener had his theory of continental drift, and he was rejected because he couldn't explain why the continents were moving. We entered into World War II. And at the time, geologists had thought that the bottom of the ocean was flat. Well, during the war, we started using sonar to watch for these German boats or submarines. And as we're watching for them using sonar, we realized that the bottom of the ocean wasn't actually flat. So it was a great discovery that was accidentally made. During the war, those U-boats, those German submarines, sank about 3,000 ships. Well, when you put a geology professor out on a boat and you give him sonar technology, he's going to do some research. So he was in charge of an attack transport ship, and he wound up using his sonar to study the ocean floor as they were out looking for these German submarines. As he's studying the ocean floor, he realizes that it's not flat, and he finds the longest mountain chain in the world. That is called the mid-ocean ridge. Now, sonar works by sending out sound waves, which hit objects, and then when they come back as an echo, those are able to be translated into what the object is that is under the water. So he used that sonar technology to study what was along the ocean floor. So the mid-ocean ridge, as I said, is the longest chain of mountains in the world. It runs along the ocean bottom, almost like seams of a baseball. It's mostly underwater. Iceland is one location where it does rise above the water, and you can see a map here of Iceland, the mid-ocean ridge going down through it. The little red triangles are representing the volcanoes. If you've ever seen Journey to the Center of the Earth, Reykjavik is where they fly into when they travel to Iceland to make their way to the center of the earth as they go through their journey. So seafloor spreading is just defined as the process where molten material is adding new oceanic crust to the ocean floor, and this happens along the mid-ocean ridge. So the molten material will come from the mantle, and because there is this crack in the ocean floor, it actually will come out and start to push the other material that's already there to the sides. Because of this, we get very young, new forming rock right along the ridge, and it's pushing the older rock away. This is creating new crust. This would be considered a constructive force. Keep in mind, those convection currents are moving, and it is causing that material that is less dense and hot to float up through and rise to the surface. It's going to push apart the older, colder stuff and move it along to the sides, kind of like that idea of the conveyor belt we discussed. So 3 forms of evidence that we have to support this idea. We have molten material along the mid-ocean ridge, we have magnetic striping, and we have drilling samples. The molten material, this would be the pillow lava that forms along the mid-ocean ridge. Basically, pillow lava is just rocks that form in the ocean water, which is very cold. It cools and hardens very quickly, and it makes these little round, almost look like puffs of rock. A lot of pillow lava is found along that mid-ocean ridge. This pillow lava tells us that we have newly forming rock, very young rock. Later on, we get into the Cold War with the Soviet Union, and the Navy is using MAD, magnetic anomaly detectors, to look for submarines under the water. Well, as they're using this magnetic anomaly detector, they realize that there are stripes along the ocean floor, and they are magnetic in nature, which is something very interesting because, as we know, the Earth has a magnetic field. So the rocks, as they're forming, have magnetic minerals in them, and as they're forming, they get trapped in alignment with the Earth's magnetic field. But what we find is that those rocks and those minerals are locked in a certain arrangement towards magnetic north and south. But over time, if you go further from the mid-ocean ridge, you're going to find a pattern where those minerals have flipped. So the rock on the ocean floor actually has this pattern of magnetic striping. They're showing where those magnetic poles of the Earth have reversed. The stripes on each side of the magnetic ridge are showing that as that rock formed, those magnetic minerals got locked into place, and then that rock split apart as new stuff came in and formed. So if you look on each side, we have stripes that actually match up. So magnetic north on the Earth is not exactly at the North Pole, and you can see by this picture, since 1831 through 2001, it has slowly moved north. We are headed for another reversal, but it won't be for a long time, won't be in your lifetime. Down here in this picture, we can see kind of what magnetic north and south look like on the Earth. And then you can see what it's going to kind of look like as it reverses. It gets kind of all jumbled up. Now, the North Pole of the Earth, the South Pole of the Earth, the physical north and south, the Earth is not going to flip, but that magnetic north and south, when we talked about magnetic poles of the Earth, that will be switching. And don't forget how we have the magnetic field of the Earth. It has to do with the outer core and those convection currents creating a current of electricity, which creates that magnetic field for us. We also have drilling samples as a piece of evidence for seafloor spreading occurring. We have had boats go out and taken drilling samples. They've actually drilled down into the crust of the Earth in the ocean floor. Remember, that is basalt. And they have found that the rocks along the ridge are much younger, and as you move away from the ridge, the rocks get older and older and older. So that implies that we have this young rock forming at the ridge, and it is pushing apart the older rock. Now, for creating new crust in one place, it has to be destroyed somewhere else, and that is through a process called subduction. Just like the word sounds, sub going under, like a submarine. So subduction means you are sinking under. So subduction is just defined as the process which oceanic crust, remember that's basalt, sinks beneath a deep ocean trench and back into the mantle. This creates trenches. You've probably heard of the Marianas Trench. It is because we have the basalt of the ocean floor colliding with the granite of the continent. The basalt is more dense, and as we know from convection currents, if it's more dense, it will sink down below. Sometimes we have ocean crust hitting ocean crust, and the rule of thumb there is older rock is colder rock. So older is colder, and therefore, as we know, colder means more dense. So the older, colder will subduct under the younger oceanic plate. So in this picture here, we have continental crust, which is the granite, less dense. We have the oceanic crust, which is more dense. And as these two collide, the oceanic, which is basalt, is more dense, and it will subduct or sink below the less dense plate. This process will cause some heating to occur, and it basically is destroying the crust.